So, hello, today we are going to talk about the geometry of latent representations. So we'll talk about the linear analogy and anisotropy and manifold aspects. And later we're going to talk about how can we use these interpretations from the geometry to build better embeddings in the future. So as a recap, one of the very promising aspects of word2vec is that they offer the nice linear analogy for those low-dimensional vectors. So previously, the semantics of words are distributed, seems like everywhere, and it's hard to describe them. But word2vec offers a nice equation. We can just do sort of vector arithmetics and use them to approximate the linear analogies of the semantics, like the vector of king minus the vector of man plus vector of woman. This vector is very close to the vector of queen. So this seems like king to man is like women to queen. Sorry, king to man is queen to women. And later, people found that this analogy contained some gender bias, because the linear analogy offers a way to poke at the word embeddings and see whether they prefer one, like whether they prefer king or queen, given the gender to be men or women. For example, this paper by Manzini is titled "Black to is criminal as Caucasian is to please." They explored a lot of gender bias in the static word embeddings using this linear analogy setting. But later, Nissim paper found that the Manzini paper contained some cases that we need to be very careful in the interpretation. So, for example, Caucasian to lawful is like black to what? And the top 5 answers are lawful, criminal, defamation, libel, vigilante. So what's reported is criminal, but if we look at the average top 5 answers, lawful actually comes ahead of criminal. So what actually is reported by the language model is that Caucasian is lawful as to black is lawful. So in this case, there's no gender, there's no race bias, because both Caucasian and black are correspond to lawful. And similarly, Jew liberal as to Christian liberal, and liberal comes ahead of conservative. And so this is one point that this paper made. We need to be very careful in interpreting this word analogy. And second, the word analogies does not just equal the semantics, because the top 5 answers, if we look at them closely, the first answer is liberal, the second answer is conservative. They are almost the opposite on the semantic coordinate. So how come there are these two positions which should be the very similar word meanings? How come these two words be on the opposite side of the semantic coordinate? So it turns out that the word embeddings are encoding the semantics in sort of a random way that we need to be more careful in the interpretation. So that are above our sort of the motivation for looking more carefully into the word embeddings geometry. So word embeddings essentially are low-dimensional embeddings. This semantic space is potentially very high-dimensional. We don't even know how many dimensions are there, but we try to approximate them with low-dimensional embeddings. And recall that one linear decision boundary cannot solve the XOR problem, because we essentially need two decision boundaries to solve that, and one linear decision boundary or one linear neurons cannot solve that. And another sort of example is that the miniest data set can be projected onto one-dimensional with 10 intervals, because this is essentially the handwritten digits from 0 to 9. And if you have some clever embedding methods like the beta variational autoencoder, then it's possible to project them onto one dimension. But this is not equal to one neuron, because there are essentially many decision boundaries out there. So there are some clever ways to do the low-dimensional embeddings, and it's a very interesting topic to look at. And this paper analyzes how many dimensions can we shrink the representation space so that the validation accuracy does not drop below 90%. So we can get sort of okay performance with much fewer parameters. So when they have, for example, more than 1,400 dimensions in the word embeddings, the validation accuracy is very high. It's close to 100%. It's like I think they have more than 90% of validation accuracy on a wide variety of tasks. But when they shrink the representation space, they are discarding a lot of information, and they found out that what's remaining in the like 600, 700 dimensional embeddings can still carry significant information about classifying this task correctly to some extent. And this is another paper that analyzes the low-dimensional representations. They looked at the skip-grams negative sampling vectors and the glowback vectors. The SGNS is just the word-to-vec, one of the two word-to-vec embeddings by Mikolov, and glowback is another static embedding method by Pennington. And they compare the word vectors from different frequency tiers with their means. So if these vectors are distributed more closely with their means, then there is essentially these vectors form a narrow cone, just as the word-to-vec vectors. So they take the mean of this, for example, top 100 frequency vectors and multiply and do the dot product of each of these vectors to this mean and plot the histogram. So we can see that the word-to-vec vectors and glowback demonstrate very different behaviors in this testing. So skip-gram negative sampling vectors are close to each other, regardless of the frequencies. And the glowback is very different, that the more frequent words are closer to each other. Because they have very, very high mean products for the high frequency words, and there are different peaks corresponding to different frequency tiers. They also compare the word vectors with each other instead of comparing them with their means in that group. So They also do the frequency tier analysis. So this result sort of corresponds to the previous histogram. So in the SGNS case, no matter what the so no matter what frequency tiers is the vectors are in, the word vectors are distributed sort of similarly away from each other. They are pointing to different directions, and their angles are larger than 90 degrees. So this results in a negative inner product. And similarly, the Glovax vectors are performing very differently between different frequency clusters. So the high frequency words are forming a cluster. So we can see that the top 100 words are forming very high inner products, very positive inner products with the other top 100 words. And as the frequencies decrease, their angles are like increasing. But saying they're pointing to different directions is like it's only a low dimensional approximation of their behavior, because we only have the notion of angles and dimensions in 3D or 2D spaces, and they are in a very high, a much higher dimensions than the 3D space. But regardless, the inner products are, the notion of inner products are generalizable to higher dimensions. And this paper analyzes the contextualized embeddings. So different from previous papers, this paper considers the whether they are the contextualized representation vectors are similar to each other, or is that more similar to SGNS vectors, or is that more similar to Glovax vectors? So this paper computes 3 scores to measure the contextuality, and they defined contextuality by sort of how variable the meaning of this word is dependent on its context. So if the word has if the word is polysemous, and it's more likely that the meaning of that word is dependent on the context. But on the other hand, if this word is has only one meaning, then it's sufficient to represent that with a static embedding. But anyway, so let's look at these 3 scores. So the self-similarity is that the mean cosine similarities between different occurrences of this word. So if this word has only one meaning, then the different occurrences of this word should be very similar. So it should have a high self-similarity. And the second score is intra-sentence similarity, the mean cosine similarity between different words within a sentence. So if a sentence is highly contextualized, then the vectors within this sentence should be highly similar to each other, regardless of the words itself, because in this case, the sentence semantic vector is sort of the sentence semantics sort of takes the higher priority than the individual constituent words. The third score is maximum explainable variance. It's the proportion of variance in the word representations for a given layer that can be explained by the first principal component. So the idea behind this is that the author wants to analyze the possibilities to use some principal components or even lower dimensions to represent the high dimensional contextualized representations. They also considered several baselines. So for the self-similarity and inter-sentence similarity, they consider the mean cosine similarity of randomly sampled words. This is necessary because if you have, for example, high self-similarity, the words, let's say the word apple in I eat an apple every day, and I'm using an Apple product. These two apples are having different meanings, but if their cosine similarity are let's say 0.9, this does not say too much about the embedding methods, because the self-similarity baseline could be like 0.5 or either 0 or either 0.97. So if the, let's say if the mean cosine similarity of two randomly sampled words have 0.97 cosine similarity, then your two apple words having 0.9 cosine similarity is basically means that these are very different meanings, and this and this embedding method considers those two occurrences of apples as two very different meanings. But on the other hand, if the baseline is 0 or is only, for example, 0.3, then if you have 0.9 of these two apple words, then this means that the representation still considers your two apples to be very similar to each other. And similarly, they also introduced the maximum explainable variance of randomly sampled word representations as the baseline for the MEV scores. So the subtract from each measure is respective baseline. So after the adjustment, they found that the average self-similarity is in general decreasing, except for the last layer of bird. So for Elmo, its layer 0 is essentially non-static. So it has, it's essentially static. It has very high self-similarity. This is because the Elmo layer 0 is essentially the output of the character-wise embedding. So there's no contextuality there. So it makes sense that whatever the word is, it outputs a corresponding fixed vector. But for the other two embeddings, like BERT and GPT-2, since the first layer, there are some effect of contextuality. And there are some additional plots about the inter-sentence similarity and the maximum explainable variance in the How Contextual Are Contextualized Embeddings paper in 2019. So another aspect of understanding the geometry is the separability of object manifolds in deep neural networks. So I'm not an expert of the manifolds, and I try to explain this. And so let's consider the linear separability of manifolds. So there are, let's say, if a layer contains n neurons and they want to represent p classes, and this setting is the n neurons represent p object manifolds, and they can define the ratio of the system load alpha to be p divided by n. So there exists a critical load value, the manifold classification capacity. So when we use a model or a system that has this classification capacity to classify less than p classes, to classify p classes that are less than AC alpha c times n, then this manifold is separable with high probability. Otherwise, this system cannot separate this many classes with high probability. So Stevenson et al. Computes the manifold geometry matrix. They also considers the manifold capacity as the decodable class information in the given data. In addition, they compute the manifold dimension dm and the manifold radius rn. So dm basically means if the manifold dimension is small, then the anchor points occupy a low-dimensional subspace, and the anchor points are the representative support vectors that determine the optimal hyperplane separating the binary dichotomy of manifolds. So I think that what the manifold dimension represents is that the is sort of the compressibility of that that manifold. So if you can represent those points in a very low dimensional space, then this manifold has a low dimension. And similarly, the Rn is, if you have a small manifold radius, then these representative points are tightly grouped to each other. Please correct me if I'm wrong in the interpretations. I'll correct the slides afterwards. And they observed that the deep neural networks ignore randomly labeled data in the earliest layers and early epochs. So they found that they have small manifold load, manifold capacity alpha, and large DM and Rn in the early layers and epochs. So they computed the unpermuted and permuted restores to test several settings of the data, and they found that the randomly labeled data which represented as the orange lines are performing very differently from other lines. So they have they use some off-the-shelf tools to estimate the alpha D and R of during the training process. And also they observed the double descent phenomenon, and during the double descent, the accuracy first drops and then recovers. And they found that as they increase the number of parameters, the accuracies drop and and then recover in the final epoch, but not the best epoch. And the Rn is approximately unchanged, and the manifold dimensions, on the other hand, is increased. So this is a nice connection between the machine learning effects and the geometry of the representations. And aside from that, we can also improve the embedding geometry, embedding quality from the observations and the interpretations we get from studying the geometry. So this paper identified some transferable hyperparameters, like in preprocessing, they used the methods like dynamic context window, subsampling, deleting real words, and association metrics, shifted pointwise mutual information, context distribution smoothing, and post-processing, add context vector, and normalization. So these methods can improve the old-fashioned SVD, or single vector decomposition embeddings on tasks. For example, word sim and simlex. So the improvements of the word embeddings in 2014, 2015 might be partially result from the hyperparameters, like the tricks they use in the preprocessing and post-processing, and their metric they choose to do. And another of them is to analyze the another transferable hyperparameter is the frequency. So this paper found that the real and frequent words are distributed far away from each other. So this is verified in the Mimno and Thompson 2017 paper, that the global vectors are putting the more frequent vectors into a closer, narrower cone than the remaining vectors. So they use adversarial training to optimize first optimize the embedding by minimizing the task loss. So this is the traditional task loss for word embedding. And second, optimize the word embedding by minimizing the discrimination loss. So this encourages the words to be distributed in a way that are indistinguishable, so that are hard to discriminate based on their frequencies. And the third is to optimize the discriminator in order to maximize the discriminating loss. So 2 and 3 forms an adversarial network pairs. So by optimizing the embedding and the discriminator jointly, they are training the discriminator to tell apart whether the embeddings of real and frequent words are distributed away. The discriminator becomes better and better in doing this, and the word embedding neural networks also become better and better in hiding this. So eventually, the word embeddings are becoming very good at hiding the difference between the frequent word and the infrequent words. So they in this way they try to sort of hide the frequency information, and they found that by using word embeddings pre-trained in this manner, they can achieve better than the state-of-the-art baselines on PentriBank, Wikitext, Text2, and better than transformer baselines on WMT and IWSOT baselines. And there are other methods to remove the remove certain information from the latent representations. For example, in 2020, Refogel proposed the iterative null space projection. We will talk about that later in the probing talk next week. And another method is to increase the anisotropy. So the idea is to inject an adversarial perturbation on the word embeddings vectors at the softmax layer. So this adversarial perturbation has a closed form solution, so you don't need to train an adversarial network anymore, given the word embeddings. And they optimize the embeddings to maximize the performance under this perturbation. So this is a very fast method, and according to the authors, this is embarrassingly simple, but they have very good performances. So in the softmax layer, the notation is a little bit different from other papers. They are using the W as the input vector to the softmax layer, and they use HT as the layer parameter. So they consider the softmax layer as the layer including the final projections from the d-dimensional vector onto the v-dimensional probabilities. So d can be between, for example, 300 to 1,000, and v is for example, 20,000. Is the size of the vocabulary. So this layer contains most of the parameters in the neural network. And this is their perturbation. They found a closed form solution, which is essentially an epsilon times the direction of h, and h is the parameter in the softmax layer. So essentially, they regularized the context vector h of that word a little bit. So for each word, they immediately knows the perturbation vector, and they add this perturbation vector into this word. And empirically, they found that let the epsilon be proportional to the Euclidean norms of each Euclidean norm of each word, and don't propagate through the delta. And essentially, this perturbation encourages the anisotropy. It's almost like a regularizer on the edge vector, and they call the edge vector the context vector. And this simple method improves the word embedding a lot, also on the PentriBank, Wikitext, and translation, etc. So another method is to post-process the word embeddings. So this is this approach also tries to increase the diversity or the anisotropy of the embeddings. So they subtracted the mean and the first several principal components. So the intuition is that the first several principal components contain the frequency information, and because the word embedding vectors are distributed within some narrow cones, if they just knock out the main components of that narrow cone, they should get more diverse distributions, and they might be able to let the subsequent networks focus less on those common dimensions. So, and it turns out that by post-processing the existing word embeddings in this manner, there are good results. So as a summary, we looked at 3 viewpoints in interpreting the geometry: the linear analogy, anisotropy, and manifold. And then we looked at several papers to use the understandings to build better embeddings.